Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Aviation Week webinar, Rugged Fiber Optic Applications to eVTOL Aircraft, sponsored by TE Connectivity. I'm David Hambling, and I'll be moderating today's event. There are just a few announcements to make before we begin. This webinar is interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speaker, download resources, and participate in the Q&A session that takes place at the end of the presentation. The slides will advance automatically throughout the event. You can also download a copy of the slides via the Resources widget. Toward the end of our webinar, we'll ask you to complete our survey found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how we can improve future events. Lastly, if you have any kind of technical problems, you can click the Help widget at the bottom of your screen, or you can type your issue into the Q&A area, and we'll be glad to give you one-on-one assistance. Now, on to the presentation. Rugged Fiber Optics Applications to eVTOL Aircraft. Discussing today's topic is Mark Benton, Senior Principal Development Engineer for Aerospace, Defense and Marine at TE Connectivity. Mark brings over 40 years of diverse R&D and product development experience in machine dynamics, electronic materials, high-speed connectors, fiber optic transceivers, media conversion, multiplexing, and rugged fiber optics. These are in markets ranging from datacom, telecom, outdoor broadcast, oil and gas, military, and commercial aviation. His main area of expertise are rugged fiber optics applications, optoelectronic transceivers and media conversion, wavelength, and time domain multiplexing. So, Mark, take it away.
Thanks, David, and I want to add my welcome to those of you wherever you are in the world today. I appreciate the opportunity to talk to you on this kind of interesting cutting-edge topic, and certainly a cutting-edge technology and market. A little bit of introduction on TE. TE overall is about a $15 billion company. It's divided up into three major segments, if you will. There's the communications segment, which is your typical datacom communication world. We have the industrial segment, which my business unit, Aerospace, Defense and Marine, is part of. And there's a transportation segment, which is far and away the largest part of the TE business. A lot of the technologies that apply to eVTOL are a combination of solutions that come from the aerospace, defense, marine side of the business, and to some degree from the automotive side of the business because of the heavy emphasis in automotive lately toward electrification of vehicles and autonomous driving. If you look at the TE overall AD&M business, it's about $1.2 billion, and you can see the split between the different market segments. There's a table here that shows the various industry standards that we participate with and we're part of, and many of the brands that you recognize in the market that are identified as TE brands. Across the business of AD&M, we have about 550 engineers and approximately an equal number of sales folks. We have those three industry focuses, and we've got 26 manufacturing sites scattered across the world in the various markets that we serve. TE overall globally is split about evenly between Asia Pacific, the EMEA region, and the North America region, and so we really like to speak to the fact that any connection can change the world. And so a little bit about today's agenda. We're going to cover 4 or 5 topics today: trends in eVTOL for fiber optic solutions and why fiber plays a role there. I'll talk a little bit about the weight advantages of fiber optic products. Talk about some challenges to handle some of the space and volume requirements. By that I mean the interesting shaped structures that you find on some of these developing platforms. How do transceivers and media converters fit into this whole architecture, and then we'll just close and have some time for Q&A. First of all, I want to get some acronyms and alphabet soup out of the way. You'll hear eVTOL and UAM and RAM and AAM, and it can get to be a little confusing. So let's just define some terms. Advanced Air Mobility, AAM, that's the market that these eVTOL and novel transportation systems are developing around. And it's heavily reliant on electrical propulsion, eventually autonomy on these things. A lot of new materials are required, a lot of distributed support infrastructure, and by that I mean ground support infrastructure for recharging and managing and maintaining these vehicles. And ultimately, it's going to have to be integrated with a unified traffic management system. You can kind of think of that like your urban air traffic control situation if you envision hundreds of these vehicles overhead. eVTOL stands for exactly what it says: electric vertical takeoff and landing. And those are aircraft that provide that advanced air mobility market, along with drones, the capability to operate between about 500 and 14,000 feet. And it's a combination of passenger movement and freight movement. And there's two kind of ranges or areas that are often talked about within AAM. That's the urban air mobility market. That's your disruptive air taxi within urban areas between towns and suburbs, and that type of application where it's readily available for people to take, much like you take, Uber or taxis or things today. And then there's a segment of regional air mobility that's really underserved by current commercial aviation, and it's a target for the electrification of more standard commercial aircraft platforms to serve that 150 to 250 kilometer range that's presently not really well served by the current aerial transport systems. eVTOLs is clearly an emerging application and market, and this is going to take some time to develop and mature. And so this slide kind of touches on the timelines that at least we're seeing at TE and we've seen from talking to others in the market. If we start on the right-hand side of the slide, these are the use cases. These are the places where people see these vehicles playing a role. So you have packages and cargo delivery. You have the air taxis that we've touched on. You have airport shuttles between, say, multiple airports and large urban areas. You have that regional air mobility market we touched on, where you have some short-range intercity flights. And then they're also looking hard at emergency and critical care applications in dense urban areas. And there's a lot of locations in the United States and in Europe and in Asia and the Middle East that are regional areas that are trying to be the pioneers for these systems, because, as I mentioned earlier, you have to have the infrastructure in place to do all the ground support and recharging and traffic management for this to be successful. Across the top, you can see a general timeline stretching from now to about 2030 and beyond. And we've seen some first certification attempts of some vehicles and first aircraft in service coming up here shortly. We think there will start to be some autonomy trials in the next year or two, and there's some demos planned around the Paris Olympics, and there's multiple other cities, as I mentioned, that are vying for demonstrations. And the expectation is by 2025, there may be hundreds of aircraft in use. As you move into the 26 to 28 period, we expect there'll be more demonstrations, there'll be more OEMs engaged in providing aircraft, and the second generation of aircraft development based on the learnings up to that point will start to take place. And finally, by the time you get to 29 and 30, the expectation is there'll be thousands of aircraft, and you're looking at a $1 to $1.5 trillion urban air mobility market. If you look at where things stand from that time period starting back about 2019 through 2023, we've seen passenger eVTOLs be demonstrated. We're seeing cargoes applications starting to be commercialized, and there's a lot of work going on in the background between the creators, the operators, the local certification regulators, working together to put together what are the certification requirements and what is the supporting infrastructure and how are we going to do traffic management. All of those things are processing in the background. The next phase will be the commercialization phase, where you'll start to see actual commercial operation of passenger eVTOLs and freight eVTOLs. There's an expectation in the 24 to 29 timeframe, you'll start to see VIP eVTOL services that would compete with your urban helicopter transport services today. The next phase, we'll start to see the scale and the growth. There'll be an expansion of the routes, the number of aircraft flying. There's an expectation in that 2030 to 35 timeframe that the operators will eventually start to become profitable as a commercial venture. And there'll have been enough success and knowledge and experience developed up to that point that the evolution of this into autonomous vehicles will start to become more of a realistic expectation. And the hope is that by that time frame, the social acceptance of this type of air transport, lots of vehicles overhead and noise and all the other considerations that have to be done will have been accepted by, the society in general, so that the overall eVTOL thing can be successful. And by the 2035 range, that's when folks expect this to really become a mature, well built out application and technology. So let's talk a little bit about fiber optic solutions in eVTOL. As you've probably heard in other presentations about fiber optics, the advantages of fiber optics don't really necessarily change with the application. It's more about how you use them. So as many of you are aware, but in case you aren't, you can find fiber optic networks running hundreds of gigabits per second over fiber cables on short runs, on long runs. The theoretical bandwidth limits of fiber are pretty much unlimited. People put that in the 200 to 500 trillion bits per second. Fiber has inherently low loss, so you can transport data over much longer distances. It's very light. Fiber tends to be a lot lighter than the equivalent copper cabling. We'll talk about some examples a little bit later in the presentation, but that can, on a vehicle level, that can factor into being a 2 to factor of 10 difference in weight for your interconnect cabling. May not sound like much, but on vehicles, as we'll see, that can be significant. Fiber's generally completely immune to electromagnetic interference and RFI and electromagnetic pulses, which makes it a lot safer in these environments. And on many of these electrically powered vehicles, you have situations where EMI can be pretty aggressive. And fiber doesn't crosstalk. You can even take advantage of multiplexing, and the different wavelengths, colors of light within a fiber don't interact with each other in general. And so you can have very high, very low speed, multiple signals on a single fiber strand, which again can reduce your cabling and increase the system performance. When you compare commercial fiber optic applications for ComAir and you look at the eVTOL applications, on the ComAir side, the drivers are pretty typically saving weight on a large aircraft, reducing the amount of space required for your cabling and interconnect. In a lot of commercial applications, bandwidth and EMI are both important. Obviously, the EMI, you don't want sensitive signals being corrupted by other noise in the environment. And the bandwidth tends to be driven on commercial aircraft by the increasing demand for in-flight entertainment, be that streaming video, be that Wi-Fi access, where you have hundreds of passengers to service on a network within an aircraft. On the eVTOL side, you have very similar drivers, weight, space, EMI, but not so much bandwidth, and we'll touch on that in a minute. But what's the difference? Well, as it was mentioned in the definition, E in the eVTOL means these are electrically powered vehicles, and so using fiber translates into less weight, and less weight in these situations typically translates into increased battery life. And battery life can mean extended range or a larger passenger load, and we'll talk about that. And the other thing that we run into in these airframes is, if you'll notice, as you look at some of the designs that are out there, they're very unique and novel structural assemblies that they're using, and there's a real constraint around space and volume on these platforms, where flat components really help. And fiber optic can play a real role there in helping you design a cable assembly or an interconnect system that fits within the available space on some of these platforms. When you look at that eVTOL application space for driving fiber optics a little more, I mentioned that it's really not about bandwidth. Well, why is that? Well, if you look at least most of the data on the critical parts of an eVTOL, it's the flight controls, the motor control systems, and those tend to be driven by fairly low speed systems like CAN bus or 10-based Ethernet, serial protocols basically that are not high bandwidth. They're tens of megabits per second, which for optical fiber is really slow. But the issue you run into is that, and on many of these platforms, you're running those signals into areas where you have DC to AC inverters, because you many times have DC battery storage, but AC motors. And those can be very challenging EMI environments that can add crosstalk and noise to your copper cabling for signal control. So there's a reason why you would go to fiber optic, even though the data rate doesn't necessarily mean you need to go to fiber optic. Also, it's not clear yet how this is going to unfold, but in the historical rotor aircraft helicopters, there are health use monitoring systems and prognostic health management systems on those platforms that involve arrays of sensors and data loggers and the like to keep track of the health of the vehicle, be it structurally, be it the motor systems and the drive components. And those tend to be arrays of sensors where a lot of data has to be collected and either online on a real-time basis or on a every flight download basis. That information has to be gathered to certify the health of the platform for the next flight. If those come to play, that's going to drive a lot more cabling on these platforms, and again, going to push the weight limits that can be affected by that. So maybe another driver to add more fiber to these networks, because you can do that with relatively less weight. And finally, it's unclear, as I said earlier, they're still working out the certification requirements. But in many cases, there are designs for certification reasons that require that critical control infrastructure on an aircraft have to be redundant and redundant with different technologies. And by that I mean you might have to have a control system that's certified using different types of media. For example, you may have a primary copper control system and a backup fiber optic system, so that one failure mode doesn't apply to both control systems, just as an example. And so those are some of the drivers that we see that can very well push us to more applications of fiber optic on these platforms. If you look at weight savings, that's another conversation that you have, again, because you're looking at battery life and that. If you look at a couple of examples, using Ethernet cables as a typical example, and you compare a duplex fiber optic cable, which is what you typically use for an optical Ethernet link, to a PVC Cat5 cable, rough order of magnitude, you'll see about 25% space savings and about a 50% weight savings, because while the cables, and the cables have different construction. So if you look at the fiber cable, you have a couple of optical fibers, you have some jacket material, you have some Kevlar strength members, and that's the cable. On the electrical side, a Cat5 cable has 4 twisted pairs, so that's 8 strands of copper. There's also copper shielding involved and a larger diameter cable overall. So you can see how it impacts the space and the weight. And you might wonder, what's the benefit? And so I did a little bit of research on this, and while this is by no means a hard and fast number, what I found was that if you're designing a flying platform, about every 150 kilometers of weight savings that you can achieve means you could add a passenger to that vehicle, or you can extend its flight time and therefore range with the designed passenger load. So there's definite advantages when you look at it at a system level to try to reduce the weight on these platforms. Another example I've come across is an application where one of the design alternatives was to connect the control system using a 5 fiber optical cable. And so just running some numbers from that application, this table kind of summarizes how much fiber cable you had, what the total weight was, and by mapping that 5-fiber cable 1-to-1 to an equivalent twisted pair cable using CAN bus, using a couple of different wire gauges, given the fact that you needed 2.5 times as much copper cable to make those connections, plus it's much heavier, you can see that the factors run around 9 to 12, so an order of magnitude, factor of 10 increase in weight for that small length of cable. So over an entire platform, that can turn out to be a significant weight advantage and start to approach some of those limits where it affects your range or affects your passenger load. Another concern that people have had in this market is the general lack of familiarity with fiber in general, and there's a lot of concern around fiber's robustness, and I think much of that has been addressed in the markets that we serve today. There's a perception that fiber cables are hard to use, they're hard to maintain, and in the markets that we serve, rugged fiber optic cabling and connectors have been qualified and used and maintained for decades in ComAir and military ground and flying applications, in space and in subsea applications. And one of the big things that's influenced that is a lot of the cable assemblies, and most of the ones that are installed on these platforms today, are not field terminated, but they're built in controlled conditions on factory assembly lines where you can test, you can maintain cleanliness, you can verify performance before they're shipped to the end user to be integrated in the platform. And therefore you can design these assemblies to provide the mechanisms you need to clean them and maintain their cleanliness during installation and build out. And the other part of that is that understanding your use case and how that particular connection is going to fit into the system, you can select an appropriate type of fiber optic connector and contact that makes the best use for the application. And so there's really two approaches that are prevalent in the market that we serve, and this is true across other markets as well. There's two basic ways you make a fiber connection. One is you do what's known as a physical contact, where you bring two typically ceramic ferrules together under a spring force, and you align them carefully, and then you couple the light across that interface. The second approach is expanded beam, and what that basically means is you draw those ferrules apart and you insert some lensing elements that basically create a collimating free space beam connection. As I like to say when folks ask me, what do I pick? My first couple of questions are generally, well, what are you trying to accomplish? How is this going to be used? Because there are advantages and disadvantages on a relative basis to each of these techniques. If you're worried about the absolute best insertion loss, a physical contact connection is generally going to do better than an expanded beam connector, although I will say over the last several years, expanded beam connectors are improving year over year, and they're starting to approach some of those limits. The same thing is true on return loss if you're using a single mode fiber and you're using the types of lasers where reflections are a concern. But you can see on this table the kind of relative merits of the various approaches. The other thing to keep in mind is how the physics works in your connector. So if this is a connection that you are going to need to make and break in the field many times because it's a data download port or something like that, then your concern about cleanliness and debris and getting that into the interface and keeping it out of the interface becomes paramount. Because if you do any kind of a mating durability test with a physical contact connector and you allow dirt ingression into that connection, you'll find over time that that insertion loss will degrade, and you will finally get to a point where it's not a if you're going to have to repair or replace that connector, it becomes a when are you going to do it, because eventually that will degrade the connection. Whereas on an expanded beam solution, you pay a little more up front for maybe less insertion loss performance, but it's consistent, much more consistent over the life of the connector, over mating durability, and over the presence of dust and exposure. And you can do a similar analysis for many of these other situations that you can run into based on what type of optical traffic you have and wavelengths on your network and how the connector is going to be installed, what kind of an environment it's in mechanically and environmentally. And you can use those use case pieces of information to make the best compromise on how you pick a connector. And then once you have that termini part of it figured out, there are many rugged, well qualified for air and other applications, form factor connector bodies that you can install either physical contact or expanded beam termini into that have been proven and qualified on many flying and other platforms for years. And so those technologies are all basically available to the eVTOL market. And it comes down to how do you pick what fits into the space and how do you pick the right ways to integrate those connections into the airframe. And that's where cable harness assemblies and optical flex circuit assemblies can come to play an important role in how you design that next level of infrastructure, the harnesses that connect the LRUs and the processors on these flying platforms. And then last but not least, of course, if you're running an optical network, you have transceivers and media converters that are converting what ultimately started as electrical signals somewhere in the system that have to be converted to light and back again. So we're going to touch on a little bit of that next as we move into the next few slides. And TE's product offering in the Aerospace, Defense, and Marine Group can help you work through all of these selections, be it our components or an integration of our components with other third-party hardware. So some of the ways you can affect getting these types of systems and harnesses installed in some of these really novel and unique looking flying platforms is a technology called optical flex circuitry. And what optical flex circuitry basically is very similar technology to the way printed wiring boards were initially made many, many decades ago, where fine wire was laid down on a substrate. Today, that fine wire has morphed into multi-mode or single-mode fiber, typically on a capped-on or some type of a flexible backing, which can then be conformally coated for resistance or up-molded, over-molded for mounting features. There's a lot of different techniques that can be applied, and they can be designed in layers where certain layers of this optical flex are tied to certain parts of your overall system. So one layer might be data monitoring, one layer might be flight control. So you can modularize the design and build out both of the flex assembly, but how you install it on the platform. And these things can solve a lot of problems with managing fiber bend radiuses in very tight corners, but you can do some other novel things with it as well. So for example, if you have a signal that is in one piece of equipment, but there's multiples of that signal that need to end up in a dozen different places, you can design shuffles and things where 12 fibers that start at one port, if you will, on the fiber network end up distributed over 12 ports at the other end of these sub-assemblies. These can give the designer some flexibility in terms of how they handle routing and net lists between enclosures on their platforms. And to be clear, flex design tends to be a bespoke system-driven design when you get down to the final physical hardware. And so the process to do that typically starts with our system folks working with your system and your harness designers to understand the constraints, which we then turn into a CAD model, which is used to drive the machinery that actually makes the optical flex circuits. And then depending on the level of integration the customer requires, it can be as simple as an unterminated optical flex circuit all the way up through that being incorporated into some kind of a connectorized enclosure, along with the breakout cables necessary to connect it further on in the network. Just depends to a large degree on what the customer's need is in terms of how we implement getting this solution into their system architecture. And then be it a cable harness, be it a fiber optic cable assembly, this is just a short list of many of the styles of already flight qualified EN connector shells and form factors that are available from ComAir experience that can allow you to do things ranging from all optical single fiber contacts, as you see things like the ARINC 801 contact here, which is an ARINC fiber flying standard. You can have combinations of that in the same shell where you supply electric connections as well as fiber connections in the same connector, which can allow you to save space. There are MT-based, which are code for mechanical transfer ferrules, which are borrowed from the datacom world, where you can have rows of 12 or 16 or 24 or 32 optical fibers in a single plastic ferrule. So you can have extremely dense multiple fiber connections where you're running pipes of traffic that doesn't need to be fanned out with a single ferrule inside the same qualified connector. And there are other versions of these connectors where you can use expanded beam single fiber contacts within that flight qualified EN4165 platform. And so as we work together, between your system designers, the TE designers, and the providers in the market, there are a lot of choices for how we can put together that fiber infrastructure to fit the application. And then finally, when you look at those form factors, it isn't just limited to the rectangular ones that you see in the traditional commercial aircraft industry, but there are military, VITA, and other standards that are flying on platforms today that take advantage of traditional D38-999 connector shells that can be used to integrate, again, multiple fiber MT contacts, single fiber physical contacts, or expanded beam contacts, depending on the use case for that connector within an eVTOL platform. And I'm not going to go through the entire list here, but TE and many others have lots of offerings that will allow you to pick the right solution that fits the space and the channel count and the available volume that you're trying to work with a rugged, well-qualified basis for your connector use case. Last topic I want to touch on briefly are transceivers and media converters, and just to give you a basic understanding of what those are and how those play in the eVTOL space. Obviously, if you're going to have a network installed on your flying platform that's using optical fiber, well, somewhere in the system inside of an LRU or other process flight controller, there's an electrical to fiber, electrical optical conversion taking place. And just to define terms a little bit, a media conversion in the traditional definition means you have changed the transport media. Well, in this case, we're saying we're changing the transport media from a copper cable to an optical fiber. But when you peel that back one level, there's really a couple of layers to that conversion that happens. Within a fiber optic transceiver, you do a media conversion. You convert electrical signals to optical signals. And you can see in the image here a fiber optic transceiver installed on a card that might be plugged into a PC or a processor. And internal to those, there are little detectors and light sources that do the actual conversion from light to electricity on the receive side and from electricity to light on the transmit side. And typically those are duplex links. You have a transmitter and receiver on both ends, and you have a fiber cable in between. When you look at those fiber transceivers, typically their electrical interface is very well defined. And there are industry standards for many of these form factors in the data communication world. But they're often part of what you consider what I call a media conversion circuit. And here's the distinction. When you look at that electrical signaling that you see at a fiber optic transceiver, it is not, in general, the same electrical signaling that you might see on your Ethernet RJ cable or your CAN bus or 10-base-100 single twisted pair Ethernet cables. There may not be the same channel count, and they're certainly not the same electrical signaling levels. And so often in a media converter, you will find some physical layer chip called a PHY chip that takes that external world electrical connection and converts it into an electrical format that a fiber optic transceiver can use to then do the final conversion back and forth to light. And that's what a media converter does. It really does that conversion for you. So for example, along the bottom here are a couple of examples of some legacy media converter solutions that use standard multi-source fiber optic transceivers for that final conversion. But you'll notice that on the green unit pair to the left, there's an RJ connection cable that brings in 4 twisted pairs of cabling. That gets ultimately translated into 2 differential electrical signals that have to drive that transceiver. The one on the right is a digital video situation, which tends to be single-ended, one direction, 75 ohm coax information, which is not easily interfaceable to a fiber optic transceiver either. And so again, you have a phi level circuit that does that conversion for you. And so when you look at media conversions and transceivers, there's some functionality like this involved in these systems that does that connection from the copper world into any of these fiber networks that you're going to find on an eVTOL or any other platform for that matter. And the other point I'll make is that a lot of the protocols I've mentioned, things like CAN bus, serial, Ethernet, those are digital protocols. They're basically 0-1. In some of the higher speed Ethernet protocols now, you have PAM4 where you have 2 bits for transition, and but it's still a digital protocol. But there are analog modulated applications, RF antennas, some RF radars, video signals can be analog modulated electrical signals, and there are analog modulated equivalent RF over fiber transceivers available to handle those kinds of systems as well. Your fiber network needs to be designed appropriately to support it, but it's certainly available and doable as a solution. The last thing I just wanted to touch on here are a couple of newer things that are in limited exposure to customers from TE that fit nicely into the eVTOL market because of their small size and modularity. We're bringing to market a very small form factor transceiver platform that leverages very high speed electrical capability out of the embedded computing market and leverages that capability into a modular pigtail transceiver offering that can be used mix and match. You can have multiple channels, you can have multiple data rates all in the same transceiver form factor. You can have uneven channel counts. By that I mean in many video applications you may need 3 feeds in one direction and 1 in reverse for control of the graphics unit, for example. And so this platform supports all of those capabilities, and it's fairly wide speed range from about 20 megabits up to as high as 12.5 gigabits per second. And so it's a platform that we're finding, because it's very small, can allow you to integrate very small form factor transceivers very cost effectively into miniaturized LRUs, which again comes back to the space and the volume constraints on these flying eVTOL platforms. The smaller you can make that hardware, the less weight it's going to take to implement the whole system, including the control hardware itself. And last but not least, we've done some demonstrations with some eVTOL partners taking advantage of some of these transceiver capabilities and marrying them up to those PHY chips so that we can create very small, very robust media conversion platforms that can interface signals as challenging as digital high definition video and as slow as megabit per second CAN bus interfaces, and interface that using fiber optic contacts and cable assemblies to run those signals over these types of platforms. And so that kind of gets me through most of the high level topics I wanted to cover. As I close, I just want to summarize a bit that, you know, within TE, I'm part of a team of engineers that is part of a systems and architecture team. And so when you look at eVTOL, it is a system and it is a brand new architecture. And we like to say that together we can work together to make eVTOL ours. And I mention that to say that within this eVTOL market, there are lots of challenges. Fiber is just one of them. There's power, there's electrical cabling, there's battery management. And so, like myself, there's others on this team that have a lot of experience and history on those other fundamental enabling technologies around eVTOL. And I just want you to be aware that there are resources on some of the links on the presentation and available on the website should your questions be more germane to those types of applications within the eVTOL application beyond fiber. And so last but not least, I want to give a shout out to one of my associates, Christoph Prell, who couldn't make the presentation today, but he's in a similar role to myself, and he's based out of the UK in EMEA. So if that's more convenient to people in the audience to reach out for more information in the EMEA market, Christoph's contact details are here. You can certainly reach out to me directly. There are links to other information both in the resources on the website for the show today and on the last slide here as well. And with that, I'm going to take a breath and turn it back over to David to see if we can do some questions and answers.
Okay. Thank you for that, Mark. Now, before we begin with today's Q&A, please can you direct your attention to our webinar survey, which is available on the right of the presentation window. If you close the survey, you can simply reopen the widget by clicking on the clipboard icon along the bottom of your screen. Thanks in advance for filling out the feedback form. Participation in the survey allows us to better serve you in future webinars. Now, on to the question and answer portion of our event. As a reminder, to participate in Q&A, just type your question into the text box located to the left of the presentation window, or click the Q&A icon at the bottom of your screen. If we're not able to answer all the submitted questions during today's webinar, we'll share them with our speaker, who can reply to you offline. Okay, so let's see what we have on the Q&A so far. Mark, what do you mean by qualified optical modules, which is a term I think you used?
By qualified optical modules, you can look at that on a couple of levels. There are qualification requirements for optical modules that are certified to fly, and the level of that is a function of, are we looking just at hardware, or is there software involved in controlling those modules? But TE sells in these markets, qualified harsh environment transceivers, and is in the process of getting the platform I just talked about qualified to some of the flying DO type and military type certification requirements. And typically at TE, we will look at the market and the applications and look at the requirements for the customers to be able to use the hardware in their applications and qualify to those standards. Right. So it's not, it all depends on the relevant standards applicable. Right. I mean, you may have ARINC standards, you may have FAA or European flight standards and the like. So it depends on the use case, but typically we take those into consideration early on in the development and make sure we're designing in a way that we can anticipate, meeting those requirements. Yeah, certainly. Okay, and I think you did actually touch on this, but perhaps you can elaborate a bit. Have you considered cybersecurity concerns, if any, about using fiber optic cables and connectors? Well, actually, to some degree, because it's a lot harder to tap and otherwise, if you will, connect to a fiber network without the system realizing that that's happened in most cases. It's relatively secure, but within TE, we have a whole team of folks that are looking at that, because you do have to consider the fact that these are flying networks. And so you need to make sure that at the system level, you may be using a fiber optic connection, but as I said earlier, there are flight controllers and things that may be networked to the outside world when you're doing downloads or connections from the vehicle to, say, some ground-based system. And that's where there's an opportunity for someone to try to get past a firewall and do something to corrupt not so much the fiber itself, but the electronics and the processors behind it that are generating those fiber optic signals. So there are, checklists and things that we look at where we're looking at these systems from that perspective. And I'll give you an example. In the transceiver world, there are diagnostic monitoring functions that can report the health of fiber optic components to the host network, be it an Ethernet switch or what have you. Those typically are closed networks. There's really no way for the outside world to interface that. But if that switch has access to the outside world and it can do anything to the software in that transceiver that's doing that diagnostics, you have to make certain that there's no way that you can corrupt any software that's controlling your optical network or impact the data in some way, right? So it depends. I mean, if this is infotainment, that's one thing. If it's flight control, that's a whole different conversation. So again, the use case matters.
Absolutely.
But we do keep an eye out for things like that because it is a consideration for some of our customers.
Right. So clearly that's something that you are familiar with and have addressed in previous applications. Okay, a question here. In addition to high levels of EMI we may face in electric vehicles, there's concern with high levels of vibration as well. Is fiber optic robust to a high level of vibration environment?
Yes, if you look at the qualification standards around any of the military applications, and it doesn't matter whether you're talking expanded beam or physical contact, single fiber connections or multiple fiber MT connections, the market has really progressed in terms of the robustness and the vibration profiles that those mated connector interfaces can withstand, and also pass traffic with pretty tight stringent requirements on continuity of signal, meaning you look for interrupts in your optical signal or your optical light levels during the vibration process. And that's a pretty standard test that's used, and many times that can also incorporate subjecting the fiber optic transceiver to that exposure as well as monitoring the fiber traffic and bit error rates during that testing. And I've been involved in many of those tests where we've successfully demonstrated over vibration levels that might have exceeded the margins, say in a DL160 case, by factors of 4 with very unconstrained, physically constrained cables, and the network not only survived the environment, but ran traffic error-free through the whole exposure. So there's a lot of experience in the market from similar but not necessarily eVTOL applications where that's been demonstrated.
Right. So when you're talking about rugged fiber optics, you're talking about rugged to vibration as well as other things.
Vibration, thermal shock, temperature cycling. There are hot and cold storage limits requirements that can be minus 55 C to 125 C. Sometimes you will see transceivers rated minus 40 to 85. But the customer may have a cold start situation where it has to start even colder than that. Might not necessarily meet the data sheet that cold, but it may have to power up and operate while the unit comes up to that minus 40 temperature. So there's a lot of demanding requirements that these systems have met.
Right, certainly. Another question here. What trends are you seeing specific to the electric vertical takeoff and landing market?
I think the trend we're seeing right now is, from a fiber perspective, it seems to be, and this is very limited data and it's very early days, and there's lots of manufacturers looking at lots of different ways to attack this problem. But it seems to be, to me, that there are two ways fiber's going to find its way into these applications. One is driven by weight and the EMI concerns around the propulsion systems, where the network will fundamentally be fiber. And by that I mean fiber into the interfaces on the LRUs and into transceivers that will be embedded in those flight controllers, which may become new flight controllers that have to be certified, that might not have any previous experience in ComAir. The other trend that we see is there are also use cases where the LRUs are certified devices, and the vendors and the OEMs don't have the bandwidth nor the time, nor do the tier 1 suppliers, to recertify those devices. So they want to find use cases where they can use those existing LRUs, but they still want to take advantage of the weight of fiber. Now you're looking at some kind of a fiber active optical cable, would be the analogy in the datacom world, way to interconnect those already certified devices in some way. And that becomes an electrical interconnect, power supply, and fiber cabling challenge that would be directed more toward a company like TE or others, where we might supply that interconnect as an end-to-end solution, for example. So I'm seeing those two trends at this point. And as the timeline said, it's early days. It's not clear that one or both or something we haven't thought of yet will ultimately be the way this shakes out as this market grows and gets more experience.
No, certainly. Okay, this next question comes in two parts. So, Mark, in your experience, are eVTOL aircraft companies thinking about fiber in the development phase of the eVTOL aircraft? And two, do you see fiber being used more in autonomous applications where more sensor data needs to be managed? So the first one is, are aircraft companies thinking about fiber in the development phase? And the second one, is it all going to be about autonomous?
Yeah, the first answer is really kind of short. It varies by OEM, but the short answer is yes. It may not be in the first generation of aircraft where they've got much more severe power supply and battery storage and other things to demonstrate, but as they look at, beyond demonstrators and flight platforms and range and things like that, fiber gets into the conversation pretty quickly. Some folks are doing it from the ground up. Others are looking at it as part of that second generation. So that's the first question. And if you step back from eVTOL for a minute and you look at autonomous automotive applications, autonomous oil and gas applications, it'll be true here too. What you typically find is that as those vehicles become more and more self-driving and autonomous, the sensor and or the processing information to control the work aspect of the vehicle goes up and up and up. And so again, you might have a fairly small platform, but you need a very fast, very lightweight, very high-speed pipe to connect all these distributed processors with some kind of a central intelligence unit that's watching all of this and making decisions on the fly about the vehicle and navigation and all of that sort of thing, interacting with other vehicles in space. And we're seeing it in automotive, seeing it in other applications in subsea. I don't see any reason why the same thing won't become true here. And frankly, there may be a lot of experience from automotive and other applications as this grows that can be leveraged by the time that becomes, we're looking 10 years out, right, for autonomy potentially in this market. There should be a fair amount of experience that can be leveraged and the early indications is yes, that'll be fiber. Right.
So as a general rule, more autonomy means you need more bandwidth, and that's going to drive people towards fiber.
Yep. Yeah, if there's any weight constraint at all, that's going to be a choice you certainly want to look at.
Which kind of takes us on to our next one. What are the unique fiber optic cable requirements for eVTOL as opposed to traditional aviation?
It comes down to really two factors. If you look at traditional aviation, you're typically building aircraft in sections, and you have designated channels where you're running all of your cabling. It's straight. It's designed for. There's space allowed for it. What we're starting to see, and it's not just true for fiber, but it's true for power distribution as well, is that the structures, and you look at the shapes of some of these vehicles, are anything but round tubes that connect from one end to the other. And so you have a lot of situations where you have to accomplish two things. You have to make very tight bends in very flat spaces, and you don't have a lot of volume to work with. And so those two factors are driving people to look at fiber constructions that allow you to make and maintain very tight bend radiuses. So bend insensitive fiber inside of loose cable constructions that allow you to bend. We find cases where the interconnect may require a ribbon fiber and an MT at the hardware, but then it has to be routed through a section of the airframe where it has to bend in two directions. And if you're familiar with flat ribbon fiber at all, it will bend very nicely in one plane, but it really isn't very bendable in the other.
Yeah.
And so there are technologies out there to be able to handle transitions from flat ribbon to loose cable that can be redirected and back to ribbon, for example, that have to be integrated into these cables that you typically don't run into in more traditional aircraft applications. It can be a ribbon and stay a ribbon. It can be a straight fiber and stay a straight fiber. You don't run into these crazy bends and turns and really restricted spaces. We've seen that in other military markets, in the AD&M market in the past, and we're starting to see where some of those capabilities apply here as well.
Right, so that's really an aspect of the whole size thing.
Mm-hmm.
Okay, here's one which I think may be asking for some clarification. Very simply, are expanded beam contacts really suitable for high vibration use cases?
Yeah, the short answer to that is yes. We have run expanded beam contacts through the same profiles that, say, the traditional 29504 contacts have been exposed, and that's true of single mode and multi-mode expanded beam connectors. And the vibration environments that they've been subjected to and the data that you see and the distributions before and after exposure are really pretty impressive. I mean, you can have expanded beam contacts that the mean data before and after exposure is sub 1 dB on contacts, and I'm talking single mode connections here. So that's been demonstrated pretty carefully. There are, if you look back at the slide, you'll notice that expanded beam is very insensitive to lateral misalignments, where you can get into trouble in vibration environments is if you get angular misalignment. Because remember, you're talking about a collimated beam, right? So if you can maintain that alignment through the vibration profile, you can get very good performance. If you don't do that, you will see degradation in vibration, even if it's just intermittent loss of signal, for example. So.
Okay. So we're getting close to the end now, so I reckon we've got time for one or two more questions. One main concern about using fiber optic is maintenance. Would you give a brief explanation about how a fiber optic repair would be done, for example, with a cable rupture?
With a cable rupture?
That's what he says.
Yeah, I mean, yeah, that can be if the cable itself between two endpoints embedded in an end frame is actually fractured or ruptures. That's going to be a challenging situation to solve, but it would be just as challenging as if you had a copper cable in that spot break in half. I think where most of the challenges you get with cables assemblies these days are not on the cable itself, but it's at the connector interface. And so, as I said earlier, there are very good, robust fiber cleaning tools that can be used during installation. Some fiber connectors can be terminated in the field, but most of the flying qualified ones, that's pretty difficult to do. And so you typically have to, have to remove that termini and repair it, or depending on the type of termini, remove the connector and repair it. And depending on what environment you're in, you may or may not be able to do that in the airframe. You may have to replace it. And there are architectures I've seen in some of these structures where people purposefully design networks so that there are like elements in the network that are identical. So you can literally do a swap between an unnecessary part or a redundant part of the system to do a very quick repair and pull the defective unit out of service and repair it in a repair facility and not try to be doing it on a flight line, for example. So there's ways to think about that and how you design the system.
Yeah, indeed. Okay, one last very quick question, because we've only got about a minute left. Can you comment on sensor applications to eVTOL propulsion or the airframe? What are some of the key enabling sensors?
Well, there's a couple of things. Obviously, in a traditional mechanical world, you can have your standard, vibration detection, monitoring, accelerometers, things like that. But when you look at composite airframe structures, there are Bragg grating-based sensors where the fiber itself becomes the sensor. And you can measure temperature, you can measure strain. And that's been demonstrated on aircraft structures and applications, and some applications already. And so when you think about that health monitoring I mentioned earlier in the presentation, those fiber-type sensors can become elements of a system like that keeps an eye on the health of the structure, or, in case of de-icing systems, temperatures of composite structures that you're trying to de-ice, for example. you don't want to overheat those. And so there's several ways that sensors like that can find their way into these. And you typically have to have the right interrogator electronics on a sensor like that to be able to make intelligence out of the reflected signals that you get. But those are capabilities that will probably find their way onto these platforms as they scale.
Right. Okay, thank you very much for that.
You're welcome.
We're about at our 1 hour now, so before we sign off, I'd like to thank our presenter Mark, as well as our sponsor, TE Connectivity. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may not have been able to listen to the event live. Thank you so much for attending, and have a wonderful remainder of your day.